Welcome back to the Atari ST Nostalgia GFA Basic tour. In the previous video we used trigonometry calculations to draw some really cool spirals, but we also saw that as complexity increased, things got quite slow actually. And in this video I want to explore how we can actually increase the performance for these graphics calculations and graphics drawing, and we will also measure the differences actually. So I've prepared some code for this to show it, some performance testing code. And basically what this program does, I took two of the routines, one from the sine and cosine drawing, graph drawing routine, and the other one I took a routine from the rosettes. And for each one I'm going to do one loop that's actually, it has the bad performance that really needs improving. Then I do a loop with the same commands but some improved, some performance enhancements. And then the third one is, I call it on steroids. I use a different routine to get the same result, and you will see that the difference is quite significant. So let's start with the first one. The first sin cos drawing. It's 1.86 ish seconds, almost 1.9. So it's not too bad, but it also seems to be quite slow compared to the performance enhancement, which is 1.76, which is already more than 5.5% faster. So that's actually already a significant improvement. But this is the one on steroids, which is 0.83 seconds, and that's like 2.25 times as fast. So that's a really big difference. And of course, if we do the rosettas again, I actually made the routine I used in the previous video. I actually added some extra mistakes in it, so you can just see how slow things get when you make stupid mistakes in your code, or when you don't regard performance when coding. And as you can see, this one took 17.3 seconds. That's actually quite slow for a 5-circle loop Rosetta. So if I improve, just use the same routine but improve on the way I code it, you can see that's actually already a significant difference. We can see the result when it's finished measuring. And as you can see, this is like 14.6 seconds. So that's like an 18% performance enhancement compared to the previous code with the same commands. Now of course, if I do the rosettas on steroids using the different routine, you can see, it's a really big difference. This was less than 5.5 seconds, which means this one is more than 3 times as fast as the first one. So where do these performance differences come from? Let me just stop the program and we can go to the procedures to see what mistakes I made, what I did to improve the performance, and how I got this stuff to run on steroids. Why is it so much faster? So first is the sin cos one. I will clear the screen. And first of all, to time it, I will use the timer command. And what the timer command actually does, basically when your Atari ST boots up, it starts the timer that counts in 200ths of a second, and it will show you the time since the system has booted up. So this command, basically I say, read the value from the timer command and put it in a variable called time, an integer variable. And then I go into the loops to draw both of the graphs. And as you can see, there's a lot of wrong here, because everywhere I'm using float type variables when it's totally unnecessary, which is very degrading for performance. And what I'm also doing is I go through an angle I from 0 to 360, and I transform it to radians, and I do it twice. I do it here, and I use this very complex formula I times pi divided by 180, which is the slowest way to do it actually, and I'm doing it twice every loop. And there's no need for that, because these and these are actually the same values, so it's very degrading for performance. And of course, after I finish the loops, I use a variable to get the seconds. So I basically get the timer command again, deduct the previous one, and divide by 200. And this one actually it has to be a float variable, because I want an accurate measurement, as you saw. It measures up to 0.005 seconds accuracy. And then I wait for a key press, but this is a really slow procedure that needs some performance enhancing, which is what I did in here. So this is exactly the same loop, but as you can see, instead of using float variables everywhere, I'm actually using word variables, because they are big enough. My number stays well within the maximum number I get for plotting and stuff is actually it's like 639. So it's a word variable is big enough, and it's just way faster. And also this same angle in radians, I calculated only once, and I put it in the formulas twice as just a number. So I don't calculate within this complex calculation, which also speeds up quite a lot. And of course I'm using a new command here. So instead of using I times pi times 180, I'm actually using a built-in command for these calculations, because GFA Basic has a lot of built-in commands to add or decrease values, or actually divide something. And if you use the built-in command, that's actually a lot faster than using just writing out the formula all the time. So how does this rat command work? I can go into direct mode, and I will clear the screen. And basically, if I want to know the radians value of an angle of 180 degrees, this is the formula I use. And as you can see, in the 180 degrees, the number of radians is actually equal to pi. And I can do it also the other way around. It's a degrees command, which basically says from this angle in radians, I want to know how many degrees it is. And in this case, the pi radians equals 180 degrees. And these calculations are way faster than when I say print 180 times pi times 180. I mean, print. I meant to divide by 180, but you know what I mean. Don't ignore this value. But it's using this built-in command is just a lot faster. And of course, I do it every time I go to this loop. So I'm doing it only once, which already makes it faster. And I'm using this command, which makes it even more fast. And I use the proper types of variables, which gave me a performance increase of more than 5.5%. But of course, putting it at steroids is a whole different story. This was twice as fast. And how did we do that? So this is exactly the same. I'm using the same variable type, so that's quite good. But we also see I use a different command here to actually get this value of the sinus of the angle. And I can put an angle in degrees in, so I don't have to do the transformation. And these commands, sinq and cosq, where the q probably stands for query, they are actually not calculating the angle. They are just getting the value from a pre-configured table. So this is a default. It's just a table lookup. And table lookups are a great way to improve the performance of your code. And these ones are actually built into GFA Basic. It's way, way faster. And it's slightly less accurate, although you can still do it up to 1/16th of a degree. So it's probably accurate enough, unless you want to do some really, really super accurate mathematical calculations. But we're not doing it here. We are just putting dots on screen. So my accuracy has to be actually accurate enough to put a dot within 640 by 400 pixels. So this is even more accurate than I even need. I don't need more than this. And this is so much faster that when you're using graphics on screen, use these table lookup commands instead of the calculation commands. We saw that it makes a lot of difference. Now, of course, in the rosettes, I made even more mistakes. What I'm doing is I'm setting the values here. These are all whole numbers, and I'm using float variables again, which is a really bad idea. And of course, then I calculate this, and I do this pre-calculations, and it's not really necessary because I know that I is 0. So this t is also going to be 0, and which means this value is going to be 0. And I know that the cosine of 0 is actually 1, and the sinus of 0 is actually 0. So these values are actually really easy to determine. So this whole row of calculations, even if I do them only once, it's totally unnecessary. So when you know what value something is going to be, don't put it in like this. And of course here I made an even worse mistake. This check is just the default check. But here, the height and the ratio in float values, I'm doing them again. I'm calculating them here inside of the loop, which means this is only a number that you only need once for the whole loop. But I'm calculating it actually like 5 times 360. So the 5 loops times 360 times I. And I'm doing this calculation. So I'm doing this calculation like 1600 times almost for nothing. And then of course here also I do this transformation to radians 4 times every loop when it's totally not necessary. I can do it 1 time. This makes it very, very slow. And of course in Rosette Better I improve on that. And what I'm actually doing, I'm using word variables again. In this case, these constants, I just calculated them once and I put the numbers here. They are hard coded because I'm not trying to change my Rosette. This is just the one I want to draw in this program. So and sometimes hard-coded is actually a good idea. I mean, this of course means I cannot ask for input again, then I will have to use variables, but in this case, I don't need it. This part is exactly the same. And of course here also, use values A and B, and actually, yeah, these constants are also sort of hard-coded. So basically I have to do the radians of I times 0.2 because I do the transformation once, and I knew that actually the small divided by the big radius is 0.2 because I used 150 versus 30. So it's a factor of 5. So this is 0.2. And I was told no, 1 minus this division is actually 1 minus 0.2 is 0.8. So in this case, B is exactly 4 times A. So I only have to calculate A once and do this very simple calculation for B instead of doing this complex computations. So I do only one radiance transformation, 2 simple calculations, and then use these values 2 times each, which is also in performance enhancement. Yeah, you saw it was 18% faster. And of course, then I do the loop. And yeah, if I go on steroids, it's basically the same performance enhancements that were also above here. And this time, instead of using radians, I use the direct angle because I use the queries again, the table lookups. And yeah, especially I'm doing 4 calculations per loop here, so it makes such a big difference in this case. Yeah, the performance difference is actually quite huge. So I think that's basically the performance tips that I can give you from this video. If you need really accurate calculations, you can use the sin and cos calculations. Otherwise, just use the sin query, which is way faster. And of course, yeah, don't use more lines of code than you need. Use the correct types of variables that you need for the purpose that you're using them for. If you have some constants that you know are not going to change, if they are dependent on user input, then get the input and then calculate them once outside of your loops. And if you don't even need to calculate them, just put them hard-coded if you need. I mean, it will make changing your code more difficult. It will make it a bit more difficult to read. But in the end, it will enhance your performance. So you always have to think about when you're programming, do I need the performance or do I need some user-friendliness or some way of easily altering it? And in this case, our goal was purely performance, so lots of hard coding. And of course, also for calculations, use the built-in functions instead of putting the formulas into your, instead of I equals I plus 1, just use inc I. It's way faster. Yeah, and especially in these ones, you could see, because this now is fast enough actually also to use graphics around probably, where before it really wasn't. So yeah, that's basically all I wanted to say in this video. Yeah, it was a very good learning experience for me again to look back and how I use performance in code. It will make me look at my code also a bit better in the future. Of course, I did the performance errors on purpose in the previous videos to actually be able to show this video on how to improve it. Although not everyone might believe me when I say that now, but it is. But it was a nice lesson in performance enhancement, which means we can use it for future videos for moving graphics around. But that's for next video, not this one. This one is finished by now, and I hope you enjoyed watching it. I hope to see you next time.